The following program is video supplemental instruction. VSI is brought to you by the Teaching Center, UF's Learning Support Center, www.teachingcenter.ufl.edu.
Okay, so I'm going to work through problem number 2 for the Physics 2020 Midterm Exam 2, year 2006. And this problem says, a raft is constructed of wood having a density of 400 kilograms per meters cubed. Its surface area is 2.5 meters squared and its volume is 0.5 meters cubed. When the raft is placed in fresh water with a density of 1 times 10 to the third kilograms per meters cubed, what percentage of it is below water level? Okay, so I've got an illustration of the problem statement here where we have a raft, and this is the total raft, and we have part of the raft that's submerged under the water. We're going to call that VB, which stands for the volume of the raft that is under the water. And we have a part of the raft that's above the water. We're going to call that VA to stand for the volume of the raft that's above the water. And we're actually asked to find the percentage of the raft that's below the water. Okay? And so actually what that's asking us is to find VB, which is the volume of the raft that's below the water, divided by the total volume of the raft, which is V sub T, times 100%, and that will give us the volume of the raft that's below the water. So this is what we're actually trying to find. Now, how are we going to go about solving this problem? Well, we need to basically go to our review formula sheet, and I encourage you to have this in order for you to refer to this as we're working through this problem. And if you can think about from class what concepts that you went over to kind of help you solve this problem, it should lead you to Archimedes' principle. Okay, and basically Archimedes' principle says that you have some buoyant force, okay, so we'll call that F sub capital B. So this is your buoyance force, and your buoyance force is actually equal to the weight, the force of the liquid, okay, that's displaced. So that's what basically Archimedes says. It says you have some object that's floating in the water or submerged in the water, and the amount of force pushing up on that object is equal to the force of the liquid that's actually displaced. And so in this particular case, since we're talking about water, we'll call that force FW, which stands for water. And so the buoyant force is equal to the force of the water, but the force of the water is just the density of the water, okay, times the volume of the water times gravity. Okay, so I'm using subscript L to designate a general liquid, so that's why we're using L. So in this particular case, the buoyant force is equal to the density of the water times the volume of the water times gravity. And you can see that if you do a unit analysis, density is going to give you mass per volume, and your volume is going to have units of volume, and gravity has units of distance per time squared. Alright? And so whenever you do the unit analysis, your volumes cancel out and you're just left with mass times distance per time squared, and that actually is a force. Okay, if you think about newtons, the SI units for newtons are kilograms meters per second squared, which is a mass times distance per time squared. All right, so that's how we get this expression for the buoyant force equaling to the volume of the liquid displaced. In this case, it's water, so that's the density of the water times the volume of the water times gravity. Okay. And so we know that from Archimedes' principle that F sub B, which is the buoyant force, is going to be equaling to the force of the liquid. In this particular case, it's the force of the water, which is equal to the force sub R. Okay, so that's equal to the force of the raft. Okay, so basically the buoyant force, the force of the raft is equal to the force of the liquid that's actually displaced. And so we know that basically the force of the raft that is below water, okay, is equal to, the force of the raft is equal to the force of the liquid that's displaced. So this is the expression that we're looking for. All right? Because the weight of the boat is equal to the weight of the liquid that's displaced. And so that's the reason why I'm using R for the raft, okay? So that's the reason why this expression is true. Now, since we can say that density of the water times the volume of the water times gravity, which is basically just the force of the liquid that's displaced, is equal to the mass of the water times gravity. Okay, so that's what that equals to. And we know that the mass of the water displaced times gravity is equal to the mass of the raft times gravity. All right? And so we know that the mass of the raft times the volume, the total volume, times G, this is actually the weight of the raft, so that's equal to this. All right? We know that that's equal to okay, so basically what I'm doing is I'm taking this expression, the weight of the water displaced, and the weight of the raft, and I'm just substituting in using our densities. All right, so basically the weight of the water is density times volume times gravity. The weight of the raft is density times volume of the total raft times gravity. All right, now what we also know is that the volume of the water displaced, which is V sub W, is equal to the volume of the boat that's under the water. Okay, so we know that V sub W is equal to V sub B, right? Because that the object is going to displace its volume. So if this part of the raft is under the water, the volume of water that it's displacing is equal to the volume of the raft that's under the water. Okay, so making some room here. if we know that this is true now, we can rewrite this equation to where we have the volume of the raft, okay, times the total volume of the raft times gravity is equal to the density of the water times the volume of the water, but that's equal to the volume of the raft that's displaced, times gravity. Okay? And if we keep in mind what we're trying to find, in this particular case we're trying to find the percentage of the raft that's actually under the water, we're actually trying to find VB divided by VT. So if we solve this equation for VB divided by VT, we get VB divided by VT is equal to the density of the raft. We know that gravities will cancel out, divided by divided by the density of the water. Okay? And so we know that VB divided by VT, if we know that the density of the raft is 400 kilograms per meters cubed, because that's what's given in the problem, and we know that the density of water is 1 times 10 to the third kilograms per meters cubed, because that's also given in the problem. All right. We can substitute that information in, where we have 400 kilograms per meters cubed divided by 1 times 10 to the third is just 1,000 kilograms per meters cubed. So all the units cancel out. Basically we're left with 4 over 10. So VB divided by VT is equal to 0.4. If we convert that to a percentage, so that means it's 40%. Alright, so using Archimedes' principle allows us to relate the force of a liquid that's displaced to the buoyance force, and knowing that principle allows us to write equations that expresses the weight of the liquid that's displaced to the weight of the raft, and doing some substitution, understanding that the volume of the liquid that was displaced is equal to the volume of the boat that's actually under the water. We were able to substitute into this particular equation, which allowed us to get an expression for the volume of the raft that's actually under water, divided by the total volume of the raft. And when we did that, it worked out to be 0.4 or 40%. All right.
The Teaching Center, UF's Learning Support Center, www.teachingcenter.ufl.edu.